Hi everyone, this video is going to be about Rutherford and his model of the atom, the third in a series of understandings about how the atom has developed over time. So to understand Ernest Rutherford, what we really need to understand is the kind of infamous experiment that he set up. So this very, very crude drawing over here is a very basic setup of the gold foil experiment that he put on to try and understand the atom and its inner workings. In your mini lesson notes, you're going to find a much better diagram, so bear with me as I sort of piece through this diagram and talk about what Ernest Rutherford observed and then what he was going to be able to conclude based on his observations from his gold foil experiment. So, as the name kind of implies, this experiment involved gold foil. And that's going to be this yellow thin sheet right here in the middle of his experimental setup. So this is just a thin sheet of gold, aka the foil. This is not very wide, like hardly visible at all. Gold has the unique property of being able to be rolled out very, very, very thin, and Rutherford used that to his advantage. And what he wanted to do with that thin sheet of gold was essentially irradiate it by blasting it with these positively charged radioactive particles known as alpha particles. So you can think of this kind of as an alpha particle gun that he had aimed at this thin sheet of gold foil. So contained in that gun is a source of alpha particles. And alpha particles we'll talk about in depth at the end of the year, but what you need to know about them right now is that they're positively charged radiation. And what's going to be nice about that is if we're shooting something that is a form of radiation, we can kind of track what happens to it over time if we have some sort of detector that our device is enclosed in. And that's exactly what Rutherford did. So let's say these radioactive particles just keep traveling in a straight line. What we're going to see is that they'll kind of light up a detector right across from where they started. So someone, probably a graduate student in some dark room, had to sit and watch this detector, some kind of film, for these radioactive hotspots that were showing up when the radiation passed through the gold foil. And if we were relying on Thomson's model of the atom at this point, since he said that the atom was this positively charged sphere with these itty-bitty little negative electrons embedded in them, what we'd expect is that these alpha particles would have no problem whatsoever passing through that gold foil because there's nothing really there to stop them. The electrons are so small that even if an alpha particle hit one of them, it would be kind of like a bulldozer hitting a pebble. No worries at all. So that was the expectation with our current model of the atom. And in fact, that's what Rutherford observed for the most part. He saw that most alpha particles pass straight through the gold foil. And what that means is all the detected particles showed up right here, right across from our source of radiation. So that was interesting. However, what was notably interesting about his experiment was that some particles didn't take this straight trajectory. Some particles were observed to show up over here, or even over here, or maybe back here, showing that their path had been more of a bouncy or deflected route. So his second observation was that some particles, very few, but some, were deflected by the foil. And remember, since the foil was so thin, it's not a result of the foil being solid. It's a result of something that composes the atoms of the gold themselves. And so Rutherford had to explain these two observations that he made, and he made two very important conclusions about the structure of the atom. First and foremost, he said, if most of them are passing straight through, that means there's nothing for those alpha particles to run into. And he took that quite literally in stating that the atom is mostly empty space. And when he said empty space, he meant empty space, complete nothingness. And this conclusion came straight from his first observation. His second conclusion was a result of the second observation he made. He said that some particles were deflected by the foil. That means not the entire atom is going to be empty space. There must be something in there that these alpha particles can either bounce off of or be deflected by. So in order to explain his second observation, what he said was that the atom must contain a small, because only a very few of those alpha particles were deflected, it must be something dense in order for those alpha particles to be able to bounce right off. And it must be positively charged, deflecting radiation that itself has a positive charge. Like charges kind of repel, so when a positive sees a positive, it's going to want to move away. So he said the atom must contain a small, dense, positively charged center. And what we're going to find is that our name for that small, dense, positively charged center is the nucleus. The nucleus of the atom was one of the key discoveries that Rutherford made. So when he was drawing out his model, what he said was, I'm going to take this idea that Thomson had, that we must have some positive charge in our atom in order to cancel out the negatively charged electrons that we know exist. And I'm going to condense all that positive charge down into one very small center. So this stands in contrast to Thomson's model, because Thomson said that positive charge was spread evenly throughout the atom. Rutherford said, no, it's very, very densely concentrated in the center of our atom. And then for the most part, the rest of the atom is completely empty space, right? We know atoms have some sort of radius, yes. And within that empty space are embedded those negatively charged electrons that J.J. Thomson talked about. Rutherford couldn't really offer us much more insight into those electrons because his experiment really dealt with this nuclear center. So what we see in this model are three key elements: the empty space, the negative electrons, and the positive nucleus. And eventually in years to come, we're going to start to discover that the nucleus itself is composed of two other subatomic particles. We've got protons that are the main contributor to the positive charge, right? Each one will have a +1 charge. And the nucleus also contains neutrons, which from its beginnings sound like a neutral type of subatomic particle, and indeed they are. They have 0 charge. So it was Rutherford's experiment that really led the way to discovering these two second subatomic particles. But the use of his particular model has led us to, again, be able to talk about the nucleus, to be able to talk about nuclear or net charge on an atom. We can talk about the positive charge in the nucleus or the overall charge of the atom itself. We can start talking about mass, because before, these negatively charged electrons were super duper tiny and couldn't really explain why an atom weighed so much. Here, if we start discovering what is contributing to that massive, not large, but dense center, we can start talking about what makes each element unique. And what's more, this is eventually going to pave the way for nuclear chemistry. That is to say, taking advantage of nuclei that are stable or unstable and start reacting them together to, yes, form energy or form weapons or whatever the case may be. We have to know about the nucleus in order to be able to talk about nuclear chemistry. So Rutherford's experiment was incredibly important. Please make sure you're familiar with his gold foil experiment, the observations he made, the conclusions he drew, and the model that he used to explain it all.